Hello, I'm Emily Donahue, and I'm going to be demonstrating the different types of ion channels. This is my roommate Maggie. She'll be playing the role of ion channel. Here she is a voltage-gated channel. The light switch and I will be portraying this cell membrane's electrical potential. The walls on either side of Maggie represent the cell membrane. As you will see, Maggie reacts to the change in light by opening up the doorway, just as a voltage-gated ion channel opens and closes in response to changes in electrical potential. Here, Maggie is representing a ligand-gated ion channel. Just like the voltage-gated channel, she is blocking the doorway so that no ions can exit or enter. Notice how this time, the channel opens in response to the ligand binding with its outer surface. Finally, here's Maggie representing a mechanically gated ion channel, and I am playing the role of the cell's internal cytoskeleton. When the cell membrane endures any stretching, pressure, or strain, the cytoskeleton tethers may be pulled taut, thus opening the channel, or pushed and loosened, thus closing the channel. Ion channels can help us explain changes in electrical potential across the cell membrane. Electrical currents move through ion channels when they are open for ion passage, and gradients create ion diffusion through passive ion channels, which are always open for certain ions. Concentration gradients want the intracellular and extracellular charges to be in equilibrium. Here's an example of a passive ion channel embedded in the phospholipid bilayer. The potassium concentration gradient drives potassium out of the cell, while the change in electrical potential drives potassium into the cell. Thus, the intracellular and extracellular charges are balanced. An influx of sodium into the cell depolarizes the cell, causing potassium to exit the cell until it returns to its resting membrane potential. Another way to think about this is as a balanced beam, with potassium represented by the green circles and sodium by the blue circles. When there's 6 green circles on each side, the balanced beam is in equilibrium. But if you add 2 sodium circles to the left side, it is now in disequilibrium. In order to balance the beam again, one green circle or potassium ion would need to exit the intracellular space and enter the extracellular space to create equilibrium again in the intracellular and extracellular spaces.